Hi, as you know, OB uses Extended Position-Based Dynamics, or XPBD, for simulation, which is what you're watching right now. I've been getting lots of questions regarding the potential integration of Augmented Vertex Block Descent, or AVBD, in OB. So in this video I wanted to share my personal experience with VBD and explain some of the reasons why I won't be pursuing it in the near future. Okay, so let's take a look at the official online AVBD demo. Apart from the usual time step size and the amount of iterations, AVBD exposes three main parameters: alpha, beta, and gamma. I will briefly explain what each of them does so you understand what I'm doing while tweaking them. So the first one, alpha, is a percentage of constraint error that will leave unresolved at the end of this step, right? So a value of 0 means every step we try to fully eliminate constraint error, but for hard constraints like contacts, this results in explosive error correction. So we need it to be a little bit higher. Instead of using alpha, we could use a post-stabilization pass, which performs one extra iteration at the end of the time step to solve positional constraints without affecting the body velocities. So if we enable post-stabilization, the alpha parameter goes away. Right? This is sort of a Baumgarten-like stabilization deal. Beta is used to increase constraint stiffness over multiple iterations to try and reach infinite stiffness, which is what we want for a hard constraint. So low values work okay, but they typically require a lot of iterations to converge, so we should crank this up quite high. In practice, if you crank this up too high, this can jeopardize the stability of the simulation. So let's go back to the default. And finally, we have gamma, which is basically warm starting. So this is the amount of constraint, stiffness, and lambda values we carry over from the previous simulation step. So this should always be less than 1, otherwise the stiffness has no way of going down over time. Setting it to 0 disables temporal accumulation entirely. So simulation steps don't carry any information to the following step, and each step is solved in isolation, basically. And as you can see, this can also greatly affect simulation stability. So let's go to the rod sample scene. Sorry, I'm going to go back to the defaults. And using the default values for all parameters, applying a force on the rod seems to result in some sort of plastic behavior. The rod retains some of the deformation instead of immediately going back to its original shape, which would be the expected result. So that's weird. Let's try and remove warm starting entirely, and if we do that, the simulation immediately explodes, right? Warm starting is generally used in engines to improve convergence speed by taking advantage of temporal coherence, but I don't really feel comfortable relying so much on it just to keep things stable. Okay, so let's just reduce warm starting instead of completely disabling it. And as you can see, at this time the simulation also breaks, so it seems we need to use very aggressive warm starting in order to get acceptable results. Okay, so let's keep warm starting on, and let's set the alpha value to 0 instead, which has the effect of fully eliminating constraint error. The simulation also becomes unstable, so let's not set it to 0, but maybe a little bit higher. And this seems to introduce quite some jittering in the simulation, and depending on your alpha value, it may not be able to recover from it, which means things just keep jittering over time. So let's try to increase the amount of iterations to see if throwing more resources at the solver allows it to converge to a solution. And it doesn't always work because depending on the amount of iterations, even with very high amount of iterations, things may explode. So using a low alpha value is generally not recommended. So basically setting alpha and gamma to 0 is almost guaranteed to make the simulation explode. And strangely enough, with fewer iterations, you tend to get more reliable results. So yeah, that's a little weird. Seems that we need to use aggressive warm starting and partial constraint accumulation solving, to keep things stable, even in a simple thing like this one. Despite using a high amount of iterations and a relatively small time step. So let's try a different scene like the rope one. So again, using a low gamma value may cause the simulation to explode. Let's pick it up. Yeah, there it goes. And even if you crank up the amount of iterations to the maximum, things may explode anyway. So let's try to go back to the default settings, and this time we will reduce the amount of iterations to something like 3. Sorry. And then reset the simulation. And this time things are stable, but the rope seems to be gaining energy over time, so it swings back to a point that's higher than the point it started from. So this keeps going on with the rope going higher and higher. So yeah, this isn't really physically correct. So yeah, I'm not sure what's causing it, because apart from iteration count, all of the parameters are right. So yeah, it's a bit weird. So in general, with AVBD, it seems like there's a very narrow combination of parameters that yields acceptable results. Let's go to, I don't know, maybe joint grid sample scene. And yeah, lowering gamma is just not an option. So yeah, this wouldn't necessarily be a bad thing if the same combination was fine for every possible scenario, as you could just hard code the parameters, but specific scenes tend to require different parameters, and the simulation doesn't seem to degrade gracefully when tweaking most of them. So I also implemented AVBD in OBI for distance constraints to evaluate ease of integration. As you can see here, for distance constraints, I go over all the constraints affecting each particle. Then I calculate the force and the Hessian matrix and accumulate them, and then finally solve a 3x3 linear system to get the position displacement, the position delta for the particle, and this yields the following results. Which are mostly okay. However, I found a very jarring artifact that you can see here, and it is that it's a sort of flattening artifact that prevents cloth and ropes from settling on a natural shape, which would be a catenary shape in this case instead of this weird V-like shape. So this can only be worked around by using a lot of iterations and substeps. I'm here using 50 iterations with 2 substeps. It seems to ease a little bit. Let's remove the jobs debugger, with 4 substeps and 50 iterations each, which is a lot of iterations. It finally subsides and it goes to the converges on the expected result. But this negates any performance improvements yielded by the AVBD method, because for natural results you just need to use a crazy high amount of iterations. Other people also report the same in their implementations. There's a Houdini AVBD plugin around, and the author also says the same thing, that flattening is a problem. I've tried reproducing this in XPBD, and I was able to, by using a particle-centric approach like VBD does. So instead of solving each local system using Newton step, I use XPBD, but the same issue takes place, right? So this artifact also seems to take place in their demo. However, since they use rigid bodies instead of particles, and rigid bodies have rotational degrees of freedom, it manifests as this sort of weird staircase artifacts. There we go. That line of rigid bodies on the left should be completely straight. However, they don't seem to be able to rotate and align themselves with the shape of the rope. I believe this is a manifestation of the same fundamental issue, but I'm not 100% sure. So if anyone can shed some more light on this, I'd be glad to hear about it. So so far my experience with AVBD has been underwhelming, to say the least. Seems to be okay for rigid body simulation, but I found it to be unreliable when it comes to cloth or ropes. I might revisit it in the future to try and find holes in my understanding of it or bugs in my implementation, but so far the comparatively higher stability of XPBD and above all its robustness in the face of arbitrary parameter combinations seems to be a better bet, at least when it comes to a game engine, right? So this is all. See you in the next video.